Hello, and welcome to our notes, section 3 in unit 4. We're going to talk about an important property of solutions, in particular as we head into the idea of acids and bases. That property is electrolytes, which is the ability to conduct electricity. I don't know if you knew that about electrolytes. And we think about electrolytes being the things in Gatorade that keep us from getting cramps, and the reason that they do that is because they conduct electricity. Seriously. So we have one kind of definition, which is the operational definition. That's sort of just what we see and how we classify. So you can be an electrolyte or not an electrolyte, and what is it that we see? What is it that we mean when we say that it is an electrolyte? And for that, we're going to write in the box just the ability to conduct electricity. So a strong electrolyte is a solution. So electrolytes have to be solutions. So I'm going to use the abbreviation SOLN for solution, so we can get all the stuff in the box. So a strong electrolyte is a solution that conducts electricity. Also, we talk about heat, so it also would conduct heat. But so it conducts very well. Okay. A weak electrolyte is going to be a solution that conducts electricity or heat just a little. And the difference between these two, very well and very little, is really big. Actually, we'll see that in a little bit. And then, of course, a non-electrolyte is a solution that does not conduct. Solution that's kind of an LN there doesn't conduct. Okay. And so then, though, we have another definition, and that is our theoretical definition, and that explains more about why, like why or how. Why is what is it about the solution that makes it conduct electricity well or not well? And so a strong light, there's kind of two, so we're going to try to get 2 bullet points in here. One idea is that it has many ions in solution. And so then, of course, a weak electrolyte would have a few ions, and a non-electrolyte would have no ions. Sorry about the crappy handwriting here. Hopefully you can get it from what I'm saying if you can't read my writing. The other idea about theoretical definition of electrolytes, why, so having ions in solution, is going to be that the solutes, remember that a solution has a solute and a solvent, and it's usually the solute that is the thing that conducts electricity. So if the solute, it's not actually whether it dissolves, we're talking about if it dissociates, if it separates, dissociates, with 2 S's, dissociates. If the solute dissociates 100%. So when you think about those ionic compounds, those metals and nonmetals, that should make sense. So if you're taking those ions, those magnets of positive and negative cations and anions, and you separate them when they dissolve, that's what we call dissociation. In a weak electrolyte, the solute is going to dissociate and here's the drastic difference. It's actually, if it's weak, it's going to be like less than 5%. That's a less than symbol, less than 5%. A weak electrolyte. So you either have 100% or you have less than 5%. And then a non-electrolyte has one of 2 conditions. Either the solute doesn't dissociate, or maybe the solute dissociates, but there are no ions in it. And that actually, both of those things are true. Us dissociating meaning separating things, and when we look at sugar, which is going to be our example down here, right? The molecules separate when you dissolve it in water, but they don't dissociate. Like here, when we have salt, and these are going to be our examples, the salt ions, the sodium ions separate from the chloride ions, right? Here, the sugar molecules separate from each other, but the carbons don't separate from the hydrogens. Okay, so both of those things are true. There are no ions, and so because of that, there's no dissociation either. Okay. My example does not actually have the light bulb, as you can see there. Yours has that awesome little light bulb. And in the light bulb, what I'm going to have you draw is like brightness on the light bulb. So when you have a strong electrolyte, and I'm going to draw this in yellow here, you have a bright light bulb, right? So we're talking about conducting electricity. That means your light bulb is really bright. If you have a weak electrolyte, you have and we're just going to put little dots around that. So this is my imaginary light bulb here. I'm putting little dots, like just a tiny bit of electricity is conducted around the light bulb. And then, of course, in a non-electrolyte, you're not going to get any light if you stick an electrode in there and try to have a light bulb conduct electricity. In terms of what's happening in the solution, when you take salt, for example, and dissolve it in water, everything that's in there, and you can draw a couple of these if you want. You have the sodium ions and the chloride ions. You have sodium ions and you have chloride ions, and everything is completely separate. So you have lots of charged particles. And these are the things that you need to conduct electricity. Electrolytes are things that have charged particles moving around. Okay, when we talk about solutions, they have to have some kind of charges, typically positives and negatives. If you're a metal, you're going to have this sea of electrons that has the electrons moving around in the metal, which is why metals conduct electricity all the time. But we're not talking about metals right now. We're talking about solutions. So in our weak electrolyte case, we have this is vinegar right here. Remember HC2H3O2, acetic acid, and you have a hydrogen. That's your metal. And so here's the thing, though. I'm going to call it, for the sense of saving space, we're going to call it H, capital H for our metal ion, and then we're going to call it AC, okay, for acetic acid. So I don't have to write the C2H3O2 over and over again. And in that solution, you're going to have mostly still HACs. And this is what happens in a weak acid. You're going to have a bunch of these HACs, acetic acids, and then maybe you're going to have one H plus, right? One hydrogen ion and one acetate ion. So I'm going to draw that down here, just an AC minus. So that's my, minus. That's my acetate ion. So less than 5% is going to be the H plus and the AC minus. Okay, so in a weak electrolyte, you do have some charges. Here's our plus charge and our minus charge, but we don't have very many. In a strong electrolyte, everything is dissociated 100%. You have lots of charged particles in there. When we talk about sugar, C12H22O11, that's table sugar. And I'm just going to use an S for sugar. Right? So yes, everything dissociates. You have all of these S's, right? I'm not dissociating, sorry. Everything dissolves. All of the S's dissolve down to their molecular level. They've mixed with the water molecules. But there are no dissociations. The C's don't separate from the H's or from the O's, and there are no ions. And so all you have are all these S's. So you have nothing, even though it's dissolved, you have nothing that conducts electricity. Okay, so now that we know what electrolytes are and what conditions are necessary for electrolytes to exist. We're going to talk about which substances make good electrolytes, strong electrolytes, and which substances don't. And there are essentially, remember we talked about types of compounds: ionic, covalent, organic, and acids. Bases is actually another kind of compound that falls kind of under the category of acids. So we're going to add those to our lists, and we're going to talk about all those kinds of compounds when they dissolve in water or don't dissolve in water, which of these solutions make good electrolytes and which ones don't. Okay, so let's start with ionics, and remember that ionic compounds or salts are substances who have a metal and a non-metal, and so you have electron transferred and you create a positive or negative ion, and then you have magnets attaching those cations to the anions. Okay, so among the salts, those that are soluble, so when we think about our conductivity table, soluble salts, I leave a little space underneath in the box, please. Soluble salts are those that are strong electrolytes. And so now we're going to learn about what's called a dissociation equation. This is quite simple. We're going to use our example here of sodium chloride, which is a strong electrolyte. Soluble salts, so here's our NaCl, so this is our dissociation equation. NaCl becomes, when it is dissolved in water, it becomes Na plus ions, and it becomes Cl minus ions, right? And when we talked about our theoretical definition of how many ions we have in solution, when we take this salt and we dissolve it in water, we end up with no salts left, and 100% of what we have in our water or in our solution that we've dissolved are sodium ions and chloride ions. So that is 100% dissociated. So the key here, I'm going to write this down here for dissociation equations. And you should write it too, dissociation equations. Okay, if they happen, you're either going to have one arrow, or we're going to see in a couple seconds you're going to have a reversible arrow. That's going to be for, essentially for, this is for strong, and this is for weak. Okay? Okay, so then for salts, something that is slightly soluble, okay, a slightly soluble salt, and we didn't have too many of those in our conductivity table, but an example is copper 1 bromide, I guess. So we're going to take CuBr, okay, and here's what happens with copper bromide, copper 1 or cuprous bromide, is that about 95% of the cuprous bromide compound actually stays together as cuprous bromide. Some of it does become copper 1, that's a plus sign, that does not look like a plus sign, and Br minus, but that's only like 5%, okay? This is 95%. 95% doesn't dissolve, so it doesn't dissociate. We saw this in some of our examples from our precipitates lab, like I think it was silver sulfate was a substance who is only slightly soluble, and so even though it's supposed to form a precipitate, it doesn't always. Okay, so that's what makes a weak electrolyte. You have a few ions in solution here, right? But most of your compound does not dissociate. Okay, and then for salts, when we have non-electrolytes, those are, of course, insoluble salts. also called precipitates. Precipitates. Ooh, that's terrible. Handwriting this pen really is hard. Precipitates. Okay, and so we can use silver chloride as an example, AgCl, and this is what you would write in lieu of a dissociation equation. So remember again that we're learning about dissociation equations, and so this one right here is a dissociation of a soluble salt, a strong electrolyte. This one here is a weak electrolyte or slightly soluble salt. And what's happening here actually is that you have these arrows mean that both of these things are happening. So it's not like there's three, 95% of your copper bromides don't do anything. They're dissolving, they're dissociating, but then they're also recombining. So this process is going on back and forth and back and forth and back and forth. And this is called equilibrium. So when you have a reversible reaction like this, both these things are happening at an equal rate, and we call this condition equilibrium. Okay, and then an insoluble or non-electrolyte, this is what the dissociation equation is going to look like. It's not an equation because nothing's happening, right? We just say, okay, this stays solid all the time. There is no dissociation. All right, so that's it for salts. Covalent compounds, they do not have any ions, so they are never electrolytes. Never. And so in our box for covalent compounds, which are always non-electrolytes, over here in the third column, we can just say that covalent compounds do not ionize. Okay, even if they are soluble. Even if they're soluble, they're not going to conduct electricity. Okay, acids and bases, on the other hand, are never non-electrolytes. All acids, if you remember, start with a hydrogen ion, and they are all aqueous. They all will dissolve in water. That's a plus. All bases are also aqueous. They all must be able to dissolve in water because in order for them to act like the acids and bases that they are, they need to be dissolved in water. Okay, so what are examples of strong and weak? A strong acid, and the definition of a strong acid is one that dissociates completely. So strong acids ionize 100%. Okay, this is what the definition of a strong acid is. So I can we'll take a simple acid like hydrochloric acid, HCl, and we're going to have one arrow because it completely dissociates. There's our H plus, and then there's our Cl minus. That's a minus sign, okay? And remember again, 100% of our solution looks like that. With a weak acid, weak acids are weak electrolytes. And the definition of weak acids are acids that ionize less than 5%. Okay? So, our vinegar up here, this was our example, right? This is a weak acid vinegar. So we take the acetic acid, it's called acetic acid, so we're going to take the HAC, that's the acetate ion, which is the C2H3O2 with the hydrogen in front, and we have to draw two arrows, right? And some of it, 5% of it, about 5%, ionizes down into its H plus and its acetate ion. But then some of it also reforms the acetic acid. So this is happening here. And you have 5% actually ionized and 95% non-ionized. Okay? Bases is exactly the same as acids. Strong bases are substances that ionize completely. Ionize completely. I'll just write complete there, I'm running out of space. An example of a strong base is sodium hydroxide, which is lye. It's the stuff they use to make soap. And it breaks down completely into sodium ions and hydroxide ions. Okay. An example of a weak base, I'm trying to think. So weak bases make weak electrolytes, just like weak acids. They only ionize, this looks exactly the same, about 5%, less than 5%. And I cannot think of an example of a weak base right now, so we'll just leave that alone. But you get the idea, I think. So what we're looking at for dissociation equations is complete dissociation for strong electrolytes. Notice that all the strong electrolytes have complete ionization. All the weak electrolytes, whether they're salts or acids or bases, have only 5% ionization, and you use the double arrows to write their dissociation equation. There are no dissociation equations for non-electrolytes because they don't ionize, they don't dissociate. And so there are no such things as acids or bases that are non-electrolytes. Salts can be non-electrolytes, but if they are insoluble, if they do not dissolve in water. That is it. Okay. Thank you, and we'll see you next time.